Welcome back, everybody. In this video, we'll be doing section 8.4, which will finish chapter 8 for us. It's going to be a lot like the last couple of sections in that we're going to be doing hypothesis testing, only this time it's for the standard deviation or variance. And so we'll be using the chi-squared distribution, but a lot of the rest of the steps are going to be very familiar. We'll write down null and alternative hypotheses. We'll calculate a test statistic. Much of the time in this section, we'll end up using the p-value method because it's, we'll use the p-value method for StatCrunch, but we'll use the critical value method if we're doing it by hand, because using the table, as we'll see, it can be a little bit awkward. So let's get started. So the things that we'll need here, N is the sample size, S is the sample standard deviation, S squared is the sample variance, sigma will be whatever the claimed, sorry, I'm getting wonky, sigma will be whatever the claimed value of the population standard deviation is, and sigma squared will be the claimed value of the variance. Requirements in order to do this, we need to have a simple random sample, which we assume we always have anyways. More important, the population has to be normal. Instead of being approximately normal with this procedure, it's more serious this time. It's a fairly strict requirement of a normal distribution. If your population isn't normal, then you get inaccurate results. So basically, you just really need to make sure that your population is normal if you're going to apply this procedure. Okay, for the test statistic, we'll be using the chi-squared equals n minus 1 s squared over sigma squared. That will be our test statistic. P-values, we can use technologies such as a calculator or StatCrunch, or table A4, which I sent you by email, I believe, and then also is on Canvas. And the degrees of freedom will be n minus 1, just as it was in chapter 7. And then we can also use critical values. Okay. So a couple of comments regarding the chi-squared distribution. Remember that the chi-squared distribution, unlike the normal distribution, isn't centered at 0. The normal distribution and t-distribution are both centered at 0, and so we end up with positive and negative z or t values. For the chi-squared distribution, the values are all positive, and so you see that it's 0 at the left end of the distribution, and all the values are positive. We saw back in chapter 7 that for that reason, we needed to look up 2 critical values whenever we were doing a confidence interval. So we'll see that we'll just have to basically be careful with it with a chi-squared distribution also. So the values are all non-negative. The distribution is not symmetric. Okay, remember that there's a different chi-squared distribution for each number of degrees of freedom, n minus 1. If you're testing claims about sigma or sigma squared, the p-value, critical value, and confidence interval methods all give the same results. With the chi-squared distribution, the p-value method is usually harder if you're going to be doing it on paper. So for this section, if you're doing it on paper, you pretty much will find it easiest if you're using the critical value method. Okay, so let's get started. Let's try one. All right, so the story for this, data set 19 in Appendix B includes volumes in ounces of a simple random sample of 36 cans of regular Coke. Those volumes have a mean of 12.19 ounces. And a standard deviation of 0.11 ounce. And they appear to come from a normally distributed population. If we want the filling process to work so that almost all cans have volumes between 11.8 ounces and 12.4 ounces, the range rule of thumb can be used to estimate that the standard deviation should be less than 0.15 ounces. So where are we getting that? The 12.4 ounces minus to 0.8 ounces, that's 0.6. So that's the range, right? And the range divided by 4 is 0.15. Back earlier in the course, we'd seen how the range rule of thumb is that the standard deviation is approximately the range divided by 4. So that's what is being used here. Rather than actually calculating that sample standard deviation, they're just saying, okay, well, it should be between 11.8 and 12.4. And so based on that, we can make the decision that the standard deviation should be less than 0.15 ounces. Okay, so it says use the sample data to test the claim that the population of volumes has a standard deviation less than 0.15 ounces. We'll use a 0.05 significance level. So where we'll begin then is picking out hypotheses and then making a picture. So let's go from there. So the null hypothesis and alternative hypothesis. We are testing the claim that the standard deviation is less than 0.15 ounces. So the null hypothesis is that it equals 0.15. Okay, since there's a less than there, it's going to end up being a left-tailed test. A little picture of the chi-squared distribution. It's a less than test, so we're going to do left. Remember with the chi-squared distribution that the area is to the right of the critical value. So what is our alpha here? Our alpha is 0.05. Okay, that means that we want an area in the tail of 0.05. So then the area to the right is 0.95. So once again, we're given an alpha of 0.05. It's a left-tailed test, so we should have 0.05 in the left tail. The area under the whole curve is 1, so 1 minus 0.05 is 0.95. Okay, our sample size is 36, which unfortunately doesn't fit in our chi-squared table. It's kind of right in the middle of 30 and 40. So we could take the average of those. Let's find the correct column though. We want 0.95 as the area to the right. So we're looking in this column. Okay, so then 30, it's 18.49. 40, it's 26.509. All right, so then we need to go get our test statistic, which is n minus 1 s squared over sigma squared. We had 36 cans. That's our n. So n minus 1 will be 35. The sample standard deviation was 0.11. And then the claimed standard deviation is 0.15. Okay, so let's see what we get. Okay, so I get 18.82. All right, so then taking a look at our critical values from the table, they're 18.493 and 26.509. So unfortunately, our test statistic is coming out really close to the lower of the two. Between 30 and 40, if we take the mean of the 18.493 and 26.509, for lack of something better to do, that would be about 22.501. So that's probably not accurate, right, for the exact critical value, but it is at least enough for us to make a decision about it. So if our test statistic is 18.82, again, remember that 0 is at the left of our picture. The test statistic would come out in that interval. And so based on that, we can reject the null hypothesis. Okay, and then our null hypothesis was that it was not less than 0.15, so that supports the claim that the standard deviation is smaller than 0.15. All right, so that was, I realized that was kind of unsatisfying about the test statistic, but that's, or rather the critical values, but unfortunately that's going to happen if we have kind of oddball degrees of freedom that don't fit into our table. Okay, let's go on to our next example. Okay, so here it says a simple random sample of 40 men, so the n will be 40 here, results in a standard deviation of 10.3 per minute. The normal range of pulse rates of adults is normally given, or is typically given, as 60 to 100 beats per minute. If the range rule of thumb is applied to that range, the result would be a standard deviation of 10 beats per minute. Again, where they're getting this is 100 minus 60 is 40. 40 divided by 4 is 10. Okay, that's where that 10 is coming from. Use the sample results with a 0.05 significance level to test the claim that the pulse rates of men have a standard deviation equal to 10 beats per minute, and we're to use the critical value method. So hypotheses first. Okay, the claim is that the standard deviation equals 10 beats per minute. So then the alternative we'll say is not equal to, so that we can have a two-tailed test. All right, our alpha is 0.05. Since our test is two-tailed, that means we should have 0.025 in each tail. Okay, let's go ahead and get the test statistic now. So we had 40 as our n, so there's 39. Our S was 10.3, and then the hypothesized was 10. Test statistic. (41.37). Okay. So now our critical values. So our alpha 0.05, two tails, makes it so that there's 0.025 in each tail. Remember that the table is going to give us area to the right. So for the right-hand critical value, the area to the right will be 0.025. So we'll be in the 0.025 column. Our n is 40, so n minus 1 will be 39. I don't have a 39. So rather than taking the mean of the rows for 30 and 40, I'm just going to use 40 because it's closer. And the difference shouldn't be enough to affect our ultimate decision. 59.342. For the left side, critical value, 0.025 is on the left, so 0.975 will be on the right. This will give us a critical value of 24.433. Okay. So then, based on that, it's pretty clear that our test statistic is not in the rejection region, and so we will fail to reject. H0. The claim this time was exactly that. This doesn't, of course, prove that H0 is true, but we've failed to prove it was false. So there's insufficient evidence. We'll say not enough. to refute the claim. Okay, again, what this is doing is a claim has been made that the standard deviation is 10. We got a sample where the standard deviation was 10.3, which is of course different. So the question you ask yourself, okay, is the standard deviation truly not 10? Or is that 10.3 just deviation due to chance? We went through the statistics here, the process, and we've concluded basically that that difference is due to chance. That's more likely than the standard deviation not being 10. Okay, another example. So here, this one is about race car drivers. There's ages of race car drivers. Most people in the general population have ages that vary between 0 and 90 years. So the range rule of thumb suggests that ages in the general population would have a standard deviation of 22.5 years. Use a 0.01 significance level to test the claim that the standard deviation of ages of race car drivers is less than 22.5 years. All right, so hypotheses first. To save us a little time, I've gone ahead and calculated the sample standard deviation. The sample is shown here. So the claim is that the standard deviation is less than 22.5 years. So then the alternative we'll say is going to include the equals case. We'll have it equal to 22.5. Okay, so then test statistic. Okay, so how many values do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 values. So n minus 1 is 14 then. Our S was 7.67. And then our claimed standard deviation was 22.5. So that 7.67 seems really different. We'll see if it's meaningfully different, okay? All right, so I get 1.62. I'll say 1.63. Okay, little picture. This one is less than in the alternative hypothesis. That will make it a left-tailed test. We're to use a 0.01 significance level. So that means that the area in the left tail should be 0.01. So to the right should be 0.99. So we're in the 0.99 column. Our n was 15. So our n minus 1 is 14. Fortunately, our degrees of freedom is actually here this time. Looks like 4.66 for our critical value. And our test statistic was 1.63. And that is in our rejection region, right? Remember that the left end is at 0 here. So it's going to be inside the interval 0 to 4.66. So based on that, we can reject the null hypothesis. Okay. And so there's evidence to support the claim. All right, so one other thing I wanted to mention about this problem, this one came out of the book. One other thing I wanted to mention about it before we go on is they've said that, okay, most people in the population have ages between 0 and 90 years. So they did 90 minus 0 divided by 4 is 22.5. And so they're saying, okay, that's the variability among the population as a whole. And so we're comparing that against the variability of drivers. In a way, though, it would make more sense because people who are 0 years old can't be drivers anyways. So in a way, it would be a lot better if we made the comparison with like 60-year-olds or 16-year-olds, sorry. So if we went 90 minus 16, which is 74, and divided that by 4, that will be 18.5. So rather than comparing 22 and a half, we really could be comparing 18 and a half. So I'll leave it to you to check and see if that would give a the same result. Okay. All right, so another thing I wanted to do with this one is show you how you could do this test using StatCrunch. So that will be coming up next. All right, so I've opened up StatCrunch and I went ahead and put in all of the ages of the 15 drivers. And so now we're ready to go ahead and do the hypothesis test for this. So we'll go up here to Stat, and then we're doing, it's standard deviation, right, that we're testing, but it goes with variance. So look under variance stats. We're doing one sample. This time I actually have the data to work with. So variance stats, one sample with data. We did this for the confidence interval in chapter 7, but this time we're going to do the hypothesis test. So select column, that's drivers. And then we're doing the hypothesis test. Now this is one part here where we're going to have to be really careful. Notice that it says right here, hypothesis test for sigma squared, okay? There's just one test in StatCrunch that does both variance and standard deviation. Our original problem, we wanted to see if the standard deviation was less than 22.5. But we need to square that because we're going to make it a variance test. 22.5 squared is 506.25. If you put in 22.5, you're going to get it wrong, okay? So 22.5 squared goes here because we're doing sigma squared. And then this was a less than, okay? And then compute. All right, so this is what we get. We get our chi-square statistic, which was calculated before as 1.62. The technology is going to virtually always give you the p-value for this. And here it's less than 0.0001, which was less than our alpha. So based on this, we would go ahead and reject that null hypothesis as we did before. All right, so before we move away from this example, I wanted to talk just a little bit more about p-value. I had said that using StatCrunch, you're going to get the p-value method. That's the way to go. If you're doing it on paper, you're probably going to find it easiest to use the critical value method. I wanted to mention, though, just how you might attempt to find the p-value on this. It takes a little bit of thinking, but I think some of you will get it just fine. So let's take a try at it. So on this, our test statistic worked out to be 1.63. Okay, so in our row for 14, which was our degrees of freedom, we don't have a 1.63, right? The lowest we have is 4.075. So if we did, we don't, but if we did have a column that would work for this particular problem, it would have to be right here, right? Notice that all the numbers in this row, 31, 29, 26, 23, and so on, they're counting down as you work from right to left. So 5.6, 4.66, 4.07. The 1.631 would have to be to the left of all those, right? There isn't one, but if there was going to be one, that's where it'd be. Now take a look at the column labels across the top. Again, this is area to the right. 0.90, 0.95, 0.975, 0.99, 0.995. Whatever would be up here would have to be more than 0.995, right? Because as you work from right to left, the labels on the columns are getting bigger and bigger. Okay, and we've determined that our column for 1.63 is going to have to be to the left of all those. So that means that the area to the right, whatever that is, has to be bigger than 0.995. Keeping in mind that the total of the area under the curve is 1, if what's on the right is more than 0.995, then what's on the left has to be less than 0.005, because again, it's going to have to add up to 1. And so we can conclude from that that our p-value is smaller than 0.005, which would be, we don't know the p, but it's enough for us to know that it's less than the 0.01, which is our significance value. If you don't fully get how we got that p-value just now, that won't be enough to stop you from answering the problems here. All the problems in the assignment should, and for the exam when the time comes, should be doable using the critical value method. All right, so let's finally go on to one more example. So here it says the television habits of 30 children were observed. The sample mean was found to be 48.2 hours per week with a standard deviation of 12.4 hours per week. So we're given the sample standard deviation. Test the claim that the standard deviation of the hours watching TV was less than 16 hours per week. Use an alpha of 0.05. So as before, we will start with null and alternative hypotheses. The claim is that the standard deviation is less than 16. Our sample was 12.4, which is less, but maybe that's just due to chance. Okay, that's what we're here to check. Okay, so sigma equals 16 will be our null hypothesis. Little picture. Okay, and then this one is going to again be a left-tailed test. Our alpha is 0.05. Our n, 30 children, so n minus 1 is 29. We actually have that. If 0.05 is the area to the left, then 0.95 will be the area to the right. So that makes our critical value 17.708. Okay, then chi-squared statistic. So then n minus 1 is 29. Our S was 12.4. Hypothesized sigma was 16. Let's see what we get. Okay, 17.418. Okay, so that's pretty close, but it is less than 17.07. Okay, so then 17.418 is less than 17.708. And so based on that, we can reject our null hypothesis. Okay, so that means there's evidence to support the alternative hypothesis. So it looks like the claim is supported. So we can just say the data support the claim. Okay. Another example. Okay, here it says a company produces metal pipes of some length, we don't know what it is, it doesn't matter, and claims that the standard deviation of the lengths is at most 1.2 centimeters. So that's the claim. One of the company's clients decides to test this claim by taking a sample of 25 pipes and checking their lengths. They found that the standard deviation of the sample is 1.5 centimeters. We're going to use an alpha of 0.05 to test that claim. The claim is that the standard deviation is at most 1.2 centimeters. So at most would be less than or equal to. We want to use, have the equal to in our null hypothesis. And so we'll make this less than. In our alternative hypothesis. All right, so once again, a left-tailed test. Our alpha is 0.05. Our area to the right is 0.95. Our degrees of freedom is 24. Area to the right, 0.95. 13.848 will be our critical value. Test statistic. Okay, so let's see if we get something more or less than 13.848. All right, so that is definitely not in our rejection region. So we can fail to reject that. Okay, and so if we're failing to reject the null hypothesis, that means that there's not enough evidence to support the claim. All right, so once again, it would be fun to think about what the p-value for this would be. So let's take a try at that. For this one, our test statistic was 37.5. So taking a look in our row for 24 degrees of freedom, we want to see where 37.5 would have fallen. So it looks like it would be right in here, okay, in between 0.05 and 0.025. Okay, so this means that this is the area to the right, remember, okay? So the area to the right is 0.05, is between 0.05 and 0.025. Okay, so this was a left-tailed test though. So what would that mean about the area to the left? Okay, it would have to be between 0.95 and 0.975. Okay, which is definitely more than what our alpha was, right? So that would be another reason, or way to see why we failed to reject that null hypothesis. All right, so next up, we have the following. A machine dispenses a liquid drug into bottles in such a way that the standard deviation of the contents is 81 milliliters. A new machine is tested on a sample of 24 containers, and the standard deviation for this sample group is 26 milliliters. At the alpha of 0.05 level of significance, we want to test the claim that the amounts dispensed by the new machine have a smaller standard deviation. So the machine originally was had 81 milliliters for its variability, right? We want to know if this 26 milliliters of this sample is truly less or is significantly less, or is it just due to chance? So hypotheses. Okay, so we want to know if the amounts dispensed by the new machine have a smaller standard deviation, smaller than the original 81. So standard deviation less than 81 equal to 81. Okay, so then let's get the critical value next. So our n was 24, so our degrees of freedom is 23. Once again, we have a left-tailed test. The level of significance was 0.05. The area to the right will be 0.95. Using our table with the degrees of freedom of 23 and an area to the right of 0.95, 13.091 will be our critical value. Test statistic. We'll have 23 for our n minus 1. Our S was 26. Our sigma was 81. 26 seems awfully low compared to 81. Let's see if that's meaningful. Okay, 2.369. Okay, so that's smaller than 13.091. Okay, in our rejection region, that is. And so we'll reject our null hypothesis. And so we can say there's enough evidence to support the claim. All right, so hopefully these are getting a little bit easier for you. Again, the p-value approach to this can be a little trickier to reason through the values in the table. So my recommendation would be to use the critical value approach wherever you can. In this one, we'll have basically a second part of it. We're going to also find the appropriate confidence interval. So we did confidence intervals back in chapter 7. So we want to see if we could do the confidence interval for this and then compare that to what we got now for our hypothesis. All right, so you may want to look back at your notes for 7.3 or the lectures from then to see how this is going to go. All right, so this is how the confidence interval plays out. Since our original test was for at the 0.05 level of significance, and that was a left tail test, that means we want an area of 0.05 in the left tail. A confidence interval is always two-sided, so if there's 0.05 in the left tail, there will be 0.05 in the right tail also. So it's really a 90% confidence interval that we're finding. So then I went through the details here. The degrees of freedom was 23. So our two critical values were 13.091, which we had already gotten. And then the other one was the 35.172, because if there's 0.05 to the right, we've got that 0.05 to the right here. So following through with the formula, we ended up with 21.03 is less than sigma is less than 34.47. So if we wanted to use that to kind of do our hypothesis test, then does our interval contain 81? Well, nowhere close, right? So that would be enough for us to reject the claim based on a confidence interval. The 81 is nowhere near that 34. All right, so our last example. So here it says the manufacturer uses a new production method to produce steel rods. A random sample of 17 rods resulted in lengths with a standard deviation of 4.7 centimeters. At the 0.10 significance level, test the claim that the new method has lengths with a standard deviation different from 3.5 centimeters, which was the standard deviation for the old method. All right, so we just want to see if the standard deviation is different. So let's start with hypotheses. So the standard deviation different from 3.5. So standard deviation equal to 3.5. You'll notice, by the way, as we do this, we haven't done anything with variance. Usually because of the units thing, we usually work with standard deviation rather than variance. So that's why all of the tests we've done so far have been in terms of standard deviation. All right, so here we're doing this at the 0.10 significance level. So that means that the area in the two tails, because it's a two-tail test, has to total 0.10. So that means that 0.05 will be in each of the two tails. Our degrees of freedom will be 16 because 17 rods were tested. So 16 for our degrees of freedom. For our critical value on the left, we have an area to the right of 0.95. So that will be 7.962 for our critical value. Then for the one on the right, there's 0.05 as the area to the right. So it will be 26.296. As the other critical value. So now test statistic. So our n minus 1 is 16. Our S, 4.7 centimeters. The hypothesized was 3.5. So let's calculate. Okay, I'm getting 28.85. So that looks like it falls in the right side rejection region. Okay, and so based on this, we can reject the null hypothesis. It looks like the evidence supports the claim. Okay. So the difference there from 4.7 centimeters down to 3.5 centimeters is meaningful. All right, so then for the second part of the question, we also wanted to find an appropriate confidence interval. So for this one, this test was two-sided, so we actually already have the two chi-squared critical values written down. So let me go ahead and fill out the rest for you. All right, so I've gone through the setup and the calculations. So as I'd said, our chi-squared right and left values we'd already figured out in the course of doing our hypothesis test. 7.962 for the left value and 26.296 for the right value. Going through the calculations, we ended up with an interval 3.66 up to 6.66. And as far as using that to help us with the hypothesis test, the claim was that it was different from 3.5, right? And so as far as our interval goes, is 3.5 inside of our interval? The answer is no. So, and we were 90% confident, right, that our interval would contain sigma, and since it doesn't, that's, we could say we're 90% confident that this interval contains sigma, which would suggest that the sigma is actually different from 3.5. All right, so that takes us actually to the end of section 8.4, and that's the end of our work on chapter 8 actually. So make sure you read through the chapter and try some of the problems. Let me know if you have any questions, and have a great day.